When the fourth rail bridge was completed in 1890, it was called the eighth wonder of the world, a potent symbol of Scottish engineering excellence. Well, in the Victorian age, the challenge was to make things big. Well, now the challenge is to make things smaller. This is the latest pride of Scotland, the microchip, and millions of them are made here every year. This is the story of the science that makes the microchip tick, and the engineering that keeps it shrinking. It's easy to appreciate an achievement like this. It's a bit harder with a microchip. The miracle is there's not much to see. The bridge has millions of rivets in it. The microchip has millions of microscopic electronic switches, and both were fabricated in Scotland. The bridge is made from steel. This is made from silicon. So the microchip, the thing that makes computers compute, is basically just humble sand, but modified by some very clever science. To get inside the microchip and explore the science, I've come to Scotland to set a challenge. Can two Scots who make a living building computers repeat the 1947 Nobel Prize-winning experiment that started the era of the microchip? Hi, Alistair, John. So what do you actually do then?
Well, we're responsible for putting these PCs together.
So you know what's inside the cream case, which is the only bit we ever see, isn't it, really?
That's right, yes. The case really houses a number of components inside, which are all required for building the machine. The main part would be the motherboard, which is housed at the back there. That really keeps everything together. This one here is the main part. That's the central processor, the CPU. That's responsible for doing all the number crunching. So that's the brain then, really? That's the brain of the machine. That's where it all happens, yes. Have you ever seen inside one of these?
Well, actually, yeah. A wee while ago we had a chip that was actually broken. To get through the ceramic, I actually smashed it with a hammer.
Subtle.
But by the time I actually got through to the chip, there was nothing left, pretty much.
You just mangled it,
That's
had
right,
you?
yeah.
We're going to ask you not to build an entire microprocessor, because you might be there some time, but a little bit of one. How do you feel about that?
Yeah, it's, you know, we're using these components every day, so it'd be interesting to see what goes inside, yeah.
Yeah, definitely.
This is the Scottish Microelectronics Centre at Edinburgh University. Hi, Alistair.
Hey,
John, you ready to build that transistor then?
Let's do it.
Come on then. It's here that Dr. Les Howarth is going to guide our volunteers as they try and make the key component of a microchip. What John and Alistair are going to build is an electronic switch called a transistor. Now, microchips are made up of millions of tiny transistor switches, which are either on or off, 1 or 0. Inside a computer, these 1s and 0s are used to represent numbers, or letters, or colours, or pretty much anything you like. The thing is, to be any good at processing information, the switch has to be able to change from on to off very quickly indeed, and that's exactly what transistors were designed to do. The transistor started life in 1947 at the research lab of the Bell Telephone Company in the USA. After 10 years of effort, William Shockley, John Bardeen and Walter Bratton invented the holy grail of electronics, a device that would amplify signals and switch very quickly. They called it the transistor. It was revolutionary and deserved a Nobel Prize because it was made out of solid material.
The significance was that for the first time electronic manipulation could be done within the solid state. The solid state is a term that many people from years ago might remember being applied to transistorized material. Up until then, valves had been used, but after that, solid state devices began to be introduced. So that was the key defining moment of modern microelectronics technology. What we're trying to do in this experiment is to replicate the original point contact transistor.
While John and Alistair take a trip back in time, I'll be looking forward to see how the transistor has shrunk so much that tens of millions of them are now squeezed onto a silicon chip like this.
We are flying over the brain of the computer, the processor. As complex as a great city, but no bigger than a fingernail.
The relentless march of increasing computer power seems endless. As transistors get smaller, computers get faster, and transistors do keep on shrinking. But how long can it continue? The future of the transistor comes later. First, a little history of very small things. The electronic switches in early computers were called vacuum valves, which were unreliable, power-hungry and bulky. The transistor would solve all these problems. No vacuum tube was needed. Instead, all the action took place inside a lump of material called a semiconductor.
What we need for this is a piece of semiconductor, and this semiconductor might be silicon, but it could also be germanium.
Shiny sides up.
So we're going to start off with a flat wafer of silicon. We're going to have a contact to the back of that. Then we're going to bring down into contact with that two gold metal contacts, which are going to contact the silicon surface, and the transistor action is going to take place between the two contacts.
In our transistor, a sheet of semiconductor, silicon, will complete a circuit between two gold plates pressed onto the surface. The flow of electrical current through the circuit is switched off and on by essentially changing the silicon from a conductor to an insulator. That amazing transformation is controlled by a current flow through a third wire connected to the back of the silicon.
The transistor is basically a switch in its very simplest form, with the two contacts on the surface of the silicon pass the majority of the current, and the amount of current which flows between those two contacts is controlled by the current which we can inject at the back contact. So we have a small current in an ideal transistor which controls a much larger current flowing between the two contacts, and that's the principle of the transistor.
How is it that we make electrical contact to the semiconductor material?
The metal contact made to the semiconductor material is quite easily. What we're going to do is use some silver epoxy. So we're going to take some glue which is loaded with silver particles, and we're going to make contact to a gold-plated base plate.
That's fine, we'll just pop it down.
Good idea, just to put a little bit of damage.
If you want to build a transistor, you soon find out about the importance of semiconductor materials like silicon.
Electronics depends absolutely on semiconductors. Without semiconductors, there would be no computers, there'd be no mobile phones, and there'd be no TV technology as we know it today.
So what is a semiconductor? Well, let's start with a conductor. That lets electricity flow through it. The most obvious example probably being a metal wire. An insulator, like plastic, is the exact opposite. It stops the flow of electricity. But instead of having this all-or-nothing behaviour, conductor or insulator, imagine a material where you can choose exactly how you want the electricity to flow through it. Now that's a semiconductor.
That's great. That's a nice one.
To make their transistor, Alistair and John are using a thin wafer of silicon as their semiconducting material. Now it's almost pure silicon, but not quite, and that not quite is very important, because by a slight but precise modification, it's been engineered to give it exactly the right electrical properties. How? Well, let's take a closer look. Electricity is the flow of subatomic particles called electrons. Now you can't see these electrons, but imagine they're like cars cruising down a main road. To increase the flow, you could add more cars, or you could remove some of the cars so that the ones that are left move more quickly. In semiconductors, you're able to control precisely how the electricity flows by adding or subtracting electrons from the material. Now, this ability to engineer electrical behavior is what makes semiconductors so useful, and this crucial process is called doping.
You intentionally introduce some impurities into the material, And the level of doping that's required is something like about 1 impurity atom in every million atoms of the host material. The interesting point is that you can actually control the level of conductivity in a semiconductor by varying the amounts of impurities that are present in the material.
Our wafer of silicon has already been doped to increase the electrical conductivity. Now it has to be wired into a circuit that'll make up the transistor. 2 metal plates with connecting wires will complete the circuit.
The idea is to fit the 2 plates together with the insulator in between them, which is going to separate the 2 contacts by this very small 50 micron distance. And then put 1 corner of each into each of these holes here and do this screw up so that it will hold them firmly. And because of the conical screws, the tighter you do the screw, the more firmly it will clamp them together, so you'll get a really good, nice, tight contact. So the first thing we have to do is to load
John and Alistair are about to learn the hard way that building a transistor this way isn't easy. It's a very fiddly job getting the right pressure of contact onto the silicon surface. The inventors knew they had to think of something better.
And they realised that a much better solution would be to incorporate the whole of the transistor action within the silicon rather than rely on the surface effect and metal contacts on the surface. And they then went on to develop that technology quite quickly, in fact, after the original experiment.
In the beginning, there was just 1 transistor, and now there's too many to count. This kind of setup was never going to be a suitable method for mass production, as our volunteers are finding out. They'd be happy to get 1 transistor to work, never mind 1 million. Fortunately, the inventors soon realised they didn't need clumsy metal pressure contacts. Instead, why not make a transistor by doping tiny regions inside the semiconductor to control the flow of electricity? The precision of this doping technique meant transistors could be shrunk down dramatically. But there was a limit to the size. A protective case and connecting wires were still needed. Transistors are crucial components in a microchip, but they're not the only ones. You need connecting wires, capacitors, and other bits and pieces to make them into a useful circuit. So the next amazing revolution in the story of the microchip was to shrink all these components down onto 1 piece of semiconductor called an integrated circuit.
The biggest step really in going from the individual transistor to where we are now was the invention of the integrated circuit. Someone had the idea to put 2 or 3 transistors onto the same piece of silicon and actually put all the connections and everything else onto that piece of silicon, so that they were actually creating a circuit without any need for soldering or anything else.
The processor has many layers. Together, these layers form millions of transistors.
In 1971, the new integrated circuit technology was used to make the first microprocessor at a fledgling company called Intel.
When Intel first introduced the microprocessor, it actually was the result of a program we had to develop chips for a calculator for a Japanese calculator company. One of our engineers saw that by making a general purpose computer on a chip, not only would it do the calculator functions, but it could be used for a variety of control applications and so forth. The whole field of computing has just been dramatically changed because of the invention of the microprocessor and its development.
The first microprocessor contained just over 2,000 transistors. Now millions more are squeezed into each new generation of chip. With more transistors inside, computers have become ever more powerful, and so has the industry that builds them. Now Silicon Valley is just part of a global engineering revolution. The heart of Scotland's electronics industry is Silicon Glen, which stretches in between Edinburgh and Glasgow. Here at this Motorola fabrication plant, they make the kind of chips you might find in your car. These days, silicon chips control just about everything from the engine to the windows. But although chips can do very different things, they're all made in pretty much the same way.
What actually happens when they construct these things is they take a wafer, which is something like about, nowadays, 20 centimetres across. So imagine a disc of silicon, and that's partitioned, so they make lots of these little circuits next to each other.
So it's actually this contact here that's not making it. So what I'm going to do is twist this round to try and get these aligned. If I just turn this screw, we should be able to twist it a little bit. That's twisted it.
Transistor technology has certainly come a long way since the early days.
That's most strange.
Oh dear. More from the boys later. Meanwhile, back to the future to find out about the struggle to make chips today. Aha! You've found me, stripped of my presenter makeup and cocooning myself in this rather lovely all-over bunny suit. Well, when it comes to chips, you've got to keep things clean. The dirtiest thing about the whole process is the people. And even a tiny flake of skin can be a huge problem on the microscopic scale of a chip.
One of the most important things in manufacturing any microelectronic device is cleanliness. And really the reason for that is because these things are so tiny.
Over a space of 1 or 2 centimetres, your electrical signal has to go through, or can go through, many millions of transistors. And each one of those transistors is crucial for the correct functioning of the chip. You could fit around about 200 transistor active areas into a hair's breadth.
Right, so it's pretty important to keep your hair on then.
Absolutely critical. This is the gowning area for our wafer fab. These suits have to go on over our everyday clothes to keep particulates and shedding materials getting into the atmosphere and potentially contaminating the products that we make.
This is one of the cleanest places on Earth, cleaner than an operating theatre.
It's more than 1,000 times cleaner. Initially it takes a little bit of getting used to, but after a couple of weeks of working in there, it's pretty comfortable. They initially look very much the same, but you get used to people's size and particular shape, the way they walk. Apart from that, each suit has got the person's name on the front of it, so if you don't recognise them from the walk, then you can just have a quick look at their name.
Okay, and this isn't looking so good because we've got a straight line along the bottom, we've got no current.
John's finding that dust can get in the way of making a good contact to silicon.
Up again, let's loosen this off a bit.
I'm sure it'll work eventually.
Appear to have nothing.
Come and have a look in here. This is one of the key areas. I mean, the first thing you notice is the colour. It's essentially a photographic process going on in here, so they use yellow light so it doesn't interfere with it. It's called photolithography, and that's where they put a pattern of all the major features they want on the microchip down onto the silicon wafer.
Basically, you project a light through a mask onto a photosensitive material, and that mask basically lays out the pattern of the transistors and the interconnecting circuitry. The photolith process defines the sizes of those devices, so it is absolutely the cornerstone of shrinking to smaller and smaller geometries.
Once the pattern's on the silicon wafer, this gas plasma etches away at the areas you don't want, creating channels in the silicon. This is where the doping process takes place, by implanting them with phosphorus or boron. And it's the precision of this process that means our transistors can keep on getting smaller and smaller. But can it continue? We'll explore the limits later. First, the good news. There's progress in the lab.
Voila, That's a diode characteristic, as we would expect from a single contact. You can see when the voltage is this polarity, we have no current flowing, and then we have some current flowing in this polarity. That's exactly the characteristic that we want. So we're winning so far. Now we've got it set up so that we can look at the other contact and see whether we've got a good contact there. So if we push the measure button again,
oops.
This isn't looking so good because we've got a straight line along the bottom, we've got no current, so it rather looks as if we've not got a contact at all. There, let's do an auto scale just to check on that. No, that's just noise again, so we've not got a good contact.
Getting two good contacts to the silicon surface is the problem.
Onto the silicon surface.
Hopefully, it's just a matter of time.
No luck yet. More of the same is called for.
After all, it took 10 years of research to make the first transistor, but since then, the pace of change has been beyond anything we've seen before.
In 1957, when they came to build a new road bridge over the Forth, new engineering techniques and materials meant it was completed in less than half the time of the old rail bridge, with only a tenth of the workforce. But progress in the microchip dwarfs that achievement. This card has a microchip inside it. You open it up, it plays you a little tune, makes you laugh, and costs about £2. But it contains more processing power than existed in the entire world before 1950. Now, if cars had progressed at the same rate as silicon chips, your average family saloon today would travel at twice the speed of sound and cost about 50p. This phenomenal progress is summed up by a remarkable prediction for the incredible shrinking chip, Moore's Law.
Hi, I'm Gordon Moore. I've spent something over 40 years in the semiconductor industry. Moore's Law is a term that got applied to a curve I published in 1965 that projected how complex integrated circuits were going to get over the next decade. That is, how many individual transistors and resistors we were going to put on a single chip. Taking the very early data, I made the bold extrapolation from about 60 components to something like 60,000 over the 10-year period. One of my friends dubbed this Moore's Law, and it's stuck ever since.
Gordon Moore looked at integrated circuits, which at the time had only been around for a few years, and he noticed that the number of devices that people were managing to put on an integrated circuit was going up roughly by a factor of 2 every year. I'm sure he didn't expect it to carry on for another 30-odd years.
I certainly didn't anticipate that it was going to continue this long. I thought extrapolating for 10 years was really a stretch at the time I did it. It certainly has been a technical challenge to keep things moving this rapidly. We've gone from single transistors to hundreds of millions of transistors in a chip in a 40-year period.
To achieve that rate of progress, the industry has relentlessly stuck to Moore's Law. That means doubling the number of transistors on a chip about every 2 years. Well, maybe that doesn't sound too hard, but let me tell you a story about doubling. Legend has it that the Emperor of China was so taken with the game of chess, he summoned the inventor to reward him. Now, the inventor's request was simple. All he wanted was 1 grain of rice on the first square of his chessboard, 2 on the second, 4 on the third, and so on, doubling for each successive square. Well, the Emperor agreed, but he had no idea how hard it would be to keep his promise. 1, 2, 3.
By the time you get to the 20th square, you're up to 1 million grains of rice, and by the time you reach the last and 64th square, you're up to something which is a 19-digit number, which is far more than the grains of rice in the whole world.
508, 509, 510, 511, 512. Fortunately, the Emperor's problem was mythical. But for microchip scientists, it's all too real. Keeping up with Moore's Law means that they have to double the number of transistors on a microchip every 18 months to 2 years. It's the equivalent of filling yet another square on the Emperor's chessboard.
In 1999, circuits with up to 250 million transistors were being produced. So that's now equivalent to being on about the 28th square of the chessboard.
And they're beginning to feel the pain.
One of the biggest practical problems is just keeping the technology going to make the devices physically smaller and smaller. Patterns on the semiconductor are defined optically and depend very much on the wavelength of light which you use.
In order to go smaller, we have to go to shorter wavelengths. It's hard to make images smaller than the wavelength of the light you're using. And that means we're working well into the ultraviolet now, and we're about at the point where there are no optical materials, no glasses or crystals that are transparent to the light we would like to use. So we're going to have to move from lens systems to all reflective systems. We use mirrors instead of lenses to make the optical systems. And we have to make them with a precision that had never been done on an industrial basis before. The mirrors will have to have better figures, more precise than the Hubble telescope has, but they'll have to be made in production quantities.
Even if the many practical problems are solved, the current silicon technology will eventually run out of steam. There is a fundamental limit. It has to do with the electrons that carry electricity around the microchip. As the width of the components shrinks to just a few atoms, the electrons start to leak out of the incredibly thin channels designed to hold them. It's as if the cars in the city suddenly started leaving the roads and randomly appearing anywhere.
There are numerous other proposals. People are looking at molecular computing, where individual molecules could function as a single electronic device, or even quantum computing, where it could be a single atom or even a single electron which performs some sort of electronic function. So the end certainly isn't in sight for Moore's law. And it's certainly a very exciting time to be a physicist.
At the end of a very long day, a new transistor is born.
Whoopee! Bingo!
Do I smell success here?
Well, the hard work has paid off. What we have here is a transistor characteristic. We've verified that we have the two contacts aligned on the silicon. We can be sure that they're both in contact.
Well done. How's it been? A piece of cake or a bit of a challenge?
I suppose it feels quite good. In the end, now that it actually works and we've seen it work.
I don't think we would have appreciated at the start just how difficult it was to get it to work reliably, so that's been a bit of an eye-opener.
How about if I wanted 9 million of them, all exactly the same, so we could make a microprocessor?
I think that would be a tough challenge.
Well, we'll let you off this time then. But well done, guys.
Your wee red light's not on.
I think John and Alistair did a superb job.
Oh, you've got the goo out of the tube.
They came in completely cold.
I'm sure they had more trials and tribulations, you know, in 1947.
But by the end of the day, they had made a working transistor.
It's only tiny, it can't be that difficult.
They can be really proud of the achievement that they had. Bingo!
Hurrah! Hurrah!